This question is about structure and bonding. Figure 1 shows part of a structure of calcium oxide, which has the formula CaO. What type of bonding is present in calcium oxide? Tick one box for 1 mark. So, let's think a little bit about calcium oxide. So, first of all, calcium is a metal, okay? And oxygen is a non-metal. Now, a specific type of bonding occurs when metals and non-metals are bonded together. And that type of bonding is ionic bonding. And the reason for this is the metals form positive ions. So what you can see here, these 2+ ions, okay, are calcium 2+ ions. And what you can see with these 2- ions here, okay, is these are O2- ions. Okay, and an ionic bond works off the transfer of electrons and that electrostatic force of attraction that occurs between the positive metal ions and the negative non-metal ions. Okay, so the answer for that is ionic for 1 mark. Figure 2 shows a particle of methane, which has the formula CH4. So we can see in figure 2, we've got a central carbon atom and 4 hydrogens bonded around it. The question asks, what type of particle is present in figure 2? Tick 1 box for 1 mark. So let's have a look at our options. So our first option is an ion. And as we just discussed, an ion is a charged particle. Okay? So ions are formed by atoms essentially gaining or losing electrons. Now, the next option is a lattice. And a lattice is actually what you could see in figure 1. A lattice is a row-like arrangement of alternating positive and negative ions. Okay, so it's not that. Now, a molecule is something which is made of covalently bonded atoms. Okay, and we'll discuss that in a minute. So the final option was a polymer. Now, the prefix poly means many. Okay, so a polygon is a shape which has many sides. So essentially a polymer is a molecule which has lots of repeated units. Okay, and examples, you see a lot of examples in organic chemistry and in plastics, for example. We've got lots of repeated units which are joined together. Okay, that's a polymer. So the correct answer to this question was actually a molecule. And the reason for this is each of these here bonds is a covalent bond. Okay? Because it is a bond between 2 non-metals, right? Carbon is a non-metal, hydrogen is a non-metal. Therefore, we do have covalently bonded atoms. So that's why the answer to this question was a molecule. Figure 3 shows the structure of C60, which we can see here. It's this funny looking ball shape. So we need to complete the sentence, choose the word from the box. So we've got diatomic, giant ionic, a fullerene, and giant metallic as our options. And the sentence is, the structure of C60 is something. So let's think about what these words mean. So the first word is diatomic. Now, di means 2, and atomic means atoms. So something which is diatomic is made up of 2 different atoms, which figure 3 is not, because it's only made of carbon atoms. Okay? Giant ionic, well, ionic, remember, involves charges. Yes, because ions are charged particles. And we can see here that C60, well, there is only carbon, right? There's no mention of any charge or attraction between metal and non-metal ions. So it's not going to be giant ionic. What about giant metallic? Well, metallic is obviously referring to metals. Well, carbon is not a metal. Carbon is a non-metal, so it's not that. So by process of elimination, we're able to work out that the correct answer is a fullerene for 1 mark. Now, this specific fullerene at C60 is something called Buckminster fullerene, or it's sometimes called a buckyball. And it's got loads of really useful applications, which are quite interesting to read up on, in things such as like pharmaceuticals and drug delivery to the body. Okay? Figure 4 shows the structure of graphite. What type of bond is labelled A in figure 4? Again, we need to tick 1 box for 1 mark. So let's think about what we already know about graphite. Well, graphite is what we call an allotrope of carbon, which means it's a form of carbon. All right? And we know, as we've previously discussed, that carbon is a non-metal. So essentially what we're looking at in A is we're looking at a carbon-carbon bond. So we're looking at the bond between 2 non-metals, which is a covalent bond. In graphite, each carbon atom forms bonds with other carbon atoms as shown in figure 4. How many electrons does 1 carbon atom use to form 1 bond? So let's think about what we know about carbon. So if we look on the periodic table, we are able to find carbon and see that it's in group 4. So what this tells us is that carbon has 4 electrons in its outer shell. These 4 electrons are all unpaired, which means that they all have the potential to form a covalent bond. And this is why, theoretically, carbon can form 4 bonds at most. Okay, carbon can't form more than 4 bonds because it doesn't have enough electrons. Now, if we look on figure 4 at graphite, I've just shown a little snippet of this below, we can see that if I pick, say, this carbon, it's bonded to this carbon. Okay, it's bonded to this carbon, and it's bonded to this carbon. So that carbon is bonded to 3 other carbons, right, as covalent bonds. So when covalent bonding occurs between 2 carbon atoms, okay, essentially they each give 1 electron. So the answer to this question is 1, because 1 carbon atom needs to give 1 electron to form 1 covalent bond. An electric current is passed through copper. Figure 5 shows the apparatus used. So we've got a DC, direct current power supply, which is basically a battery. Then here we've got a circuit, so we've got a filament bulb, which lights up, and we have the copper here. So we've got another complete the sentence question, choose the answer from the box. So we've got gas, liquid, solid, solution is our choice. And the sentence says, figure 5 shows the copper conducts electricity as a what? Okay, so we're thinking about the state of matter. Now, the first part of eliminating for this question is basically a bit of common sense. Would you be able to mould a gas or a liquid to specifically that shape as you can see in figure 5? Well, no, you wouldn't be able to. Okay, the gas would just go all over, it would diffuse, and the liquid wouldn't be able to be stored as it can be seen on figure 5. Now, a solution means it is dissolved. Again, not what you can see on figure 5. So figure 5 is showing copper as a solid. Okay, and that's the correct answer for 1 mark. And if you know about your metallic structure, then that makes sense. Okay, because the metallic structure has these rows of positive ions and then these delocalized electrons, which are the reason why metals conduct electricity, because the delocalized electrons are free to move around the structure and carry charge. Okay, so not a very scientific approach really of looking at figure 5, rather more of a common sense question really, that one. So another complete the sentence. Copper conducts electricity because of the movement of delocalized watts. So we've got atoms, electrons, ions, molecules. Well, I've sort of spoiled the answer to this question in the previous one, and the answer is electrons. Okay, because as I said, in the metallic structure, we have these rows of positive metal ions, these delocalized electrons, which are free to move around the structure and carry charge. Okay, it couldn't be atoms, right? Because an electric current is a flow of charge and atoms aren't charged. Okay, ions, well, yes, ions are charged, but the ions in a metal are what are stationary, and molecules, again, not charged. Figure 6 shows the apparatus used to investigate the effect of electricity on sodium chloride solution. Now that word's really important. So let's look at figure 6. So we've got another direct current power supply, filament bulb. It's very similar to what we saw in figure 5, except this time we haven't got a solid metal rod. Instead, we've got the sodium chloride solution. Complete the sentence. So it says figure 6 shows that sodium chloride conducts electricity when what? Well, the key to this question was looking at the use of language. Sodium chloride solution, right? Sodium chloride solution. So remember, a solution means that it is dissolved. Okay. Gaseous means it's a gas, obviously. And molten means that it's been melted. Well, we can see in figure 6 it's none of these things. But in fact, it is a sodium chloride solution. So the sodium chloride has been dissolved. Sodium chloride is made up of ions. So we now know sodium chloride features ionic bonding. Figure 7 shows the apparatus used to investigate the effect of electricity on solid sodium chloride and molten sodium chloride. So we can see this here is the solid sodium chloride, and it says that the filament bulb does not light up. And on the right hand side here is the molten sodium chloride, and it says here that the filament bulb does light up. So table 1 shows the results. So the solid sodium chloride, as we said, it does not light up. So this shows that it does not conduct electricity, whereas the molten sodium chloride bulb did light up, and this shows that it does conduct electricity. Because essentially here, the circuit is incomplete. There's a gap in the circuit because this doesn't conduct electricity. Whereas with the molten sodium chloride, the circuit was complete. Okay, because the molten sodium chloride did conduct electricity. So we need to draw one line from each statement to the correct reason. So let's start by thinking about solid sodium chloride. So as we said, sodium chloride is ionic. So we've got this lattice arrangement, okay, of positive and negative ions. And what we can see is that they are fixed in place. All right. Now, if you think to physics, if you've covered electricity in physics, you might know that current is essentially the movement of charged particles. So essentially here, the solid sodium chloride won't conduct electricity because there are no charged particles which are able to move, right? The ions are fixed. Whereas molten sodium chloride does conduct electricity because the ions are mobile, right? When it's molten, those ions are a bit more free to move. And because ions are charged particles, right, they carry charge, that is where you get your electric current from, okay? That molten, those are ions being able to move around the structure. This question is about the halogens. Which group in the periodic table is known as the halogens? Tick one box for 1 mark. So our options are group 1, group 2, group 7 and group 0. Now the correct answer for this question was group 7, okay, for 1 mark. So I'm just going to highlight the group 7 elements here in yellow. Now, group 1 is the alkali metals. Group 0 are the noble gases. Okay, and we don't really cover much about group 2 at GCSE. So that leaves group 7. Now, as a sort of interesting point, the word halogen is Greek for salt former. Okay? And what do group 7 elements do? Well, when a group 7 element reacts with metals, they will form salts. Okay, so that's just a little bit of interesting knowledge as to why we call the group 7 elements the halogens. A fluorine atom has 7 electrons in the outer shell. Okay, that makes sense, doesn't it? Because we've just established that halogens are in group 7. Figure 8 shows part of a dot and cross diagram to represent a molecule of fluorine, which has the formula F2. Now we need to complete the dot and cross diagram, and we only need to show the electrons in the outer shells for 2 marks. So what we're looking at here is F2. We've got 2 fluorine atoms bonded together. We're looking at covalent bonding, aren't we? Yeah, because it's 2 non-metals which are bonded together. So they're covalently bonded. And remember, covalent bonding is all about sharing electrons. Okay? So, let's think about these fluorine atoms then. So let's think about fluorine. So fluorine's in group 7, which means it has 7 electrons in its outer shell. So let's show that outer shell. So first of all, we put the electrons in unpaired, and then we start to pair them up. So we get something like that. So now let's draw another fluorine atom, and this time I'm going to use dots instead of crosses. And we can see something like this. Now hopefully what you can see in these fluorine atoms that I've drawn is that this electron and this electron are unpaired. So what could happen is we could have these electrons as our shared electrons. Okay, so each fluorine could share that electron, and essentially that would mean that each of the fluorines would have a full outer shell. So we'd have a cross and a dot in the middle, and then we'd have 6 electrons in each of the individual atoms. So then if you look at this, so if we just look at this fluorine here, we've got 1, 2, 3, 4, 5, 6, 7, 8. And then if we look at this fluorine here, we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay? So in this question, you got 1 mark for showing this shared pair of electrons. Okay, that was worth 1 mark. And then the second mark came from noticing that there were 6 other electrons on each atom. Chlorine reacts with potassium bromide solution. Complete the word equation. So what we're seeing here is a special type of reaction called a displacement reaction. Now what a displacement reaction is it's when a more reactive halogen replaces a less reactive halogen's place in a compound. So what we're seeing here is chlorine reacting with potassium bromide. Now chlorine is more reactive than bromine. So what this means is chlorine will take bromine's place in potassium bromide. So what you're going to end up with is you're going to end up with bromine and then potassium chloride. Now it's really important that you indicate that it's bromine, okay, not bromide, and it's chloride, not chlorine. Now the reason for that is this here will be like bromine gas, okay, whereas this here is potassium chloride, in which case the chloride is representing the Cl- ion. Okay, so it was a 2 mark question. You got 1 mark for saying bromine and 1 mark for saying potassium chloride. So as I've just said, what type of reaction happens when chlorine reacts with potassium bromide solution? So it's the reaction we've just looked at, which I said was a displacement reaction. Okay, and the reasoning for that is displacement reactions are when a more reactive halogen replaces a less reactive halogen in a compound, which is exactly what we just completed on that word equation. Complete the sentence. Choose the answer from the box. So we've got an atom, an electron, a neutron, a proton, and our statement says chlorine is more reactive than bromine. This is because chlorine gains something more easily. So we're talking about reactivity here. And whenever we're talking about reactivity, we're going to be talking about an electron. Okay? Or multiple electrons, as the case may be. So what we did in figure 8 when we were talking about the covalent bond and the sharing of electrons, okay, this is an example of when we're talking about reactivity. Okay, could it be an atom? Well, could chlorine gain an atom? No, probably not. And a neutron and a proton, well, they've got nothing to do with reactivity. Okay, so the correct answer for 1 mark was an electron. The next question asks, how does the size of a chlorine atom compare with the size of a bromine atom? We need to complete the sentence. So the sentence says, a chlorine atom is what a bromine atom. So is it bigger than, the same size as, or smaller than? So to understand this, we're just going to look at the periodic table. So if we find chlorine, which is here, and we're comparing that with bromine, which is here. So hopefully you're able to see that bromine is lower down the periodic table than chlorine. So what that means is that bromine is a bigger atom than chlorine. And that's because as you move down the groups of the periodic table, okay, you add a new electron shell. So bromine has one extra shell than chlorine does. So just from using the periodic table, we can say that a chlorine atom is smaller than a bromine atom. And that's the correct answer for 1 mark. So this next question asks us to explain our reasoning behind why chlorine is smaller than bromine. So as I just explained using the periodic table, chlorine has fewer shells than bromine. Okay, and that's the answer that I would probably go for. There were alternate answers on the mark scheme, which included things like chlorine has fewer electrons. Okay, that's still correct. That's still a valid reason. Okay. Or obviously you could have said the opposite, but for bromine. So you could have said bromine has more shells than chlorine, or you could have said bromine has more electrons than chlorine. The other thing you could have said was actually to be a bit more descriptive. So where I've said here chlorine has fewer shells than bromine, you could have explicitly said that chlorine has 3 shells and that bromine has 4 shells. Okay, and you can find that information by looking at what period it is in on the periodic table. Okay, so a few alternative answers that would have been allowed in this question. Fluorine reacts with chlorine to produce ClF3. Balance the chemical equation for the reaction. So we've got Cl2 plus something F2 makes 2 ClF3s. So the way I would approach balancing this equation is to make a table. So the atoms that we've got present are Cl and F. Now remember that the number of Cl atoms has to be the same on the left and the right. And that's the same with the number of F atoms, okay, fluorine atoms. You need to have the same number of fluorine reactant atoms as fluorine product atoms. So let's start by thinking about the chlorine. So we've got 2 chlorines on the left and 2 chlorines on the right, okay, because it's 2Cl, okay? Now, let's think about the fluorines on the right-hand side. So remember that we've got ClF3, but we've got 2 of them. So essentially we've got 2 3s, which is 6. And at the minute, on the left-hand side, we've got F2. So the question is, how do we get from 2 to 6? Well, we need to times it by 3. This question asks us to explain, okay, so use scientific reasoning to explain why fluorine is a gas at room temperature. And we need to use the words energy, forces, molecules, and weak in our answer. So let's think about fluorine. What type of structure is fluorine? Well, fluorine is a simple covalent molecule, right? It's made up of covalent bonds. Now, these covalent bonds are actually really, really strong. They're very hard to break. But what we need to appreciate is that when we're changing state, so when we are boiling, okay, to turn it into a gas, we are not actually breaking those covalent bonds. Instead, we are overcoming the forces which hold together the different fluorine molecules. And these forces are called intermolecular forces. Intermolecular meaning between the molecules. So what I've written here is that there are weak intermolecular forces between the molecules, and these weak intermolecular forces require little energy to overcome. So, just to check, I've included energy in my answer, I've included forces, I've included molecules, and I've used the word weak. Right, so this question was a 3-mark question. Now, the first mark was awarded for saying there are weak forces, and the second mark was awarded for saying between the molecules. Now, I've used the phrase weak intermolecular forces, which is actually perfect for 2 of those marks. And then the final mark was for saying requires little energy to overcome. This question is about acids and bases. Which ion is found in all acids? Tick 1 box for 1 mark. So what I've shown down here in the purple pen is some examples of different acids. So I've got here HCl, which is hydrochloric acid, H2SO4, which is sulfuric acid, and HNO3, which is nitric acid. And then besides it, I've broken them down into their ions. So I've said HCl is made up of a H plus and a Cl minus. I've said that H2SO4 is made up of 2 H pluses and an SO42 minus ion. And that HNO3 is made up of a H plus ion and an NO3 minus ion. Now, hopefully you're able to see that all these acids have H plus ions, okay? And that is what makes an acid an acid. Okay, all acids have H plus ions present. Zinc nitrate can be produced by reacting an acid and a metal oxide. Name the acid and the metal oxide used to produce zinc nitrate. And this is for 2 marks. So let's start by thinking about the metal oxide. Well, any metal oxide's name ends in oxide. Okay? And it is the metal oxide. And in this case, the metal in our salt is zinc. Okay, the first word of the name of a salt is always the metal. So therefore, our metal oxide is zinc oxide. So now let's think about the acid. So we're looking to produce zinc nitrate. So we need to get nitrate ions from somewhere. So where can we get nitrate ions on? Well, we could use nitric acid, okay, which has the formula HNO3. Okay, so your nitrate ions are your NO3 minus ions. In an equation, zinc nitrate is written as ZnNO3 2, AQ. What does AQ mean? Tick 1 box for 1 mark. So AQ is an example of a state symbol. Okay, and in chemistry we have 4 state symbols that we use. We have S for solid, L for liquid, G for gas, and AQ, which stands for aqueous. Okay? An aqueous solution. And what aqueous solution means is it means dissolved in water. The pH of a solution is 8. Some hydrochloric acid is added to the solution. Suggest the pH of the solution after mixing. So this is a suggest question, which means that there are more than one right answers. Okay, so let's think about a pH of 8. So I've just shown the pH scale here at the bottom of the screen, and hopefully we can see that 8 is here. Okay, it's just above 7, which is the neutral pH, so we could say that it's a weak alkaline. Now, it says in the question that some hydrochloric acid is added to the solution. So what's going to happen to the pH if we add acid? Well, it's going to become more acidic, isn't it? So the pH is going to be less than 8. So an answer that I might go for would be something like 5. But in the mark scheme, it says to allow any value from 0 to less than 8. Okay, so anything which is classed as acidic on the pH scale, or 7, neutral, would have been fine for that 1 mark. Table 2 shows the solubility of 3 solids in water at room temperature. Okay, so we've got phosphorus oxide, silicon dioxide and sodium hydroxide, and then we can see here the mass of the solid that dissolves in 100 centimeters cubed of water. Okay, so that's 50 grams for phosphorus oxide, 0 grams for silicon dioxide, and 100 grams for sodium hydroxide. So straight away, looking at that data, we can say that silicon dioxide is insoluble. Okay, because none of it dissolves in water. The teacher labelled these 3 solids A, B, and C. She gave a student the information shown in Table 3. So in Table 3, we've got solid A, B, and C. And then we've got the observation when added to water. So we can see that solid A and B make colourless solutions. And in C, the solid does not dissolve. So that's interesting. So the solid does not dissolve. And we said that silicon dioxide was insoluble. So therefore, we can say straight away that C is going to be silicon dioxide. Okay. Now, the other bit of information we're given in Table 3 is the pH of the solid in water. So for A, it's 14. For B, it's 2. And for C, it's 7. So C is going to be neutral. Okay, but we don't need to worry about that because we've already established that C is silicon dioxide. So let's look at A and B. So a pH of 14 is going to be an alkali, and a pH of 2 is going to be an acid. Okay, so we need to establish now, out of phosphorus oxide and sodium hydroxide, which is the alkali and which is the acid. Well, sodium hydroxide has the formula NaOH. And hopefully you can see that obviously in NaOH we have OH minus ions. which therefore means that sodium hydroxide is going to be A. Therefore, phosphorus oxide must be the acid. Okay? So what we've done there is we've used our understanding of pH, we've used our understanding of solubility to figure out which solid, A, B and C, is phosphorus oxide, silicon dioxide and sodium hydroxide. So the question asks us to describe a method that could be used to identify each of the three solids A, B and C. You must use an indicator in the method, and we need to use information from table 2 and table 3. So basically in our answer we just need to write out our thought process that we used earlier. So the first step I would write is to dissolve solid A, B and C in water. Okay, so this is so we can determine their solubility. And remember, what we found was that silicon dioxide is insoluble. So given that piece of information, we can say that solid C is silicon dioxide. Now, remember, to determine between A and B, we needed to look at pH. So here is where we're going to add our indicator, and that indicator is going to be a universal indicator. And we're going to add that to solutions A and B. Now for A, the indicator will turn a purple or a blue colour. And this is because solid A is an alkali. Therefore, A is sodium hydroxide for reasons that we discussed earlier. Now for B, the indicator will turn red as it's an acid. Therefore, using a process of elimination, B has to be phosphorus oxide. Okay, so what we've done in our answer there is we've mentioned the indicator, universal indicator, and we've broken down for solid A, B and C to identify which is which. Okay, now this was a 4-mark question, and in the mark scheme it was looking for a method that would lead to a valid outcome, which this is. It was looking for a method which had key steps outlined, and it wanted those key steps outlined in a logical sequence. And I think doing it like I have here, in almost like bullet points or a list of the 5 steps, makes it really clear to the examiner. We have mentioned the indicator, universal indicator. So this is a perfect model answer that would have scored 4 marks. This question is about the elements in group 2 of the periodic table. Figure 9 shows the positions of 4 elements, A, B, C and D, in the periodic table. So let's have a look at figure 9. So let's think about what a group is. Now, in the periodic table, our groups are the vertical rows. Okay, so we say that this is group 1, this is group 2. Now this bit in the middle here, we call these the transition metals. Okay, so then we say we have group 3 here, group 4, group 5, group 6, group 7, and then this is group 8, or it's sometimes called group 0. So they are the groups, right? The vertical columns. And then remember that the periods are these horizontal rows. So this first question asks, which element is in group 2? So let's look at group 2 And hopefully we can see that element B is the only one in group 2 for 1 mark. Group 2 metal carbonates break down when heated to produce a metal oxide and a gas. So we can see here we've got metal carbonate makes metal oxide and gas. Name the 2 products when calcium carbonate, which we're told has the structure CaCO3, is heated. So we are told our metal carbonate, we're told that is calcium carbonate. So we need to figure out what is the metal oxide going to be and what is the gas going to be. So let's start with the metal oxide, that's probably easiest. So in this instance, the metal is calcium. Okay, calcium is the only metal out of these atoms, calcium, carbon and oxygen. So the metal oxide has got to be calcium oxide. And then to figure out what the gas is going to be, let's think about which atoms we have not used up. So if I was to tell you that calcium oxide has the formula CaO, we could think, okay, so we've used up this calcium, we've used up 1 oxygen, so essentially, what atoms have we got left? We've got 1 carbon atom and 2 oxygen atoms. So we get CO2, which is carbon dioxide. Okay, so that was a 2-mark question. You get 1 mark for the metal oxide and 1 mark for the gas. What type of reaction happens when a compound breaks down? So another word for something breaking down is decomposing. Okay, therefore, is it going to be burning, decomposition, neutralization or reduction? Well, it's going to be decomposition. Okay, so in chemistry, we use this term decomposition to describe a reaction when we are breaking down a compound. Okay, decomposition also means when something is rotting or something is decaying. Okay, so that's a little link you could have made there as well. The metal carbonate takes in energy from the surroundings to break down. What type of reaction takes in energy from the surroundings? So we need to tick 1 box for 1 mark, and our options are combustion, electrolysis, endothermic or exothermic. So let's work through these one by one. So combustion. So let's think about combustion as when we burn something in oxygen. So just a bit of common sense would think that if we burn something, we're letting off heat. So it's not going to be that. Electrolysis. Well, electrolysis is when we are splitting up a compound using electricity. So it's not that. So we're left with endothermic and exothermic, which looks promising because thermic means heat. So endothermic, exothermic. An exothermic reaction is a reaction which lets off heat. And the way I remember that is exo is a bit like exit. So when you're going out the exit, you're leaving a room. So an exothermic reaction is when heat is being given off. Therefore, the correct answer was endothermic. So an endothermic reaction is one where we take in energy from the surroundings. Figure 10 shows the volume of gas produced when a group 2 metal carbonate is heated. So what we've got in figure 10 is the volume of gas in decimeters cubed on the y-axis and the mass of group 2 carbonate heated in grams on the x-axis. Now what I've just pointed out here in purple is that on the y-axis every small square represents 0.4 decimeter cubed, and on the x-axis every small square represents 2 grams. So this first question asks, the student collected 5.2 decimeters cubed of gas. What mass of the group 2 metal carbonate is heated? So what I've done here in this purple pen is I've found 5.2 decimeters cubed on the y-axis, which I've said is here. And then I've used a ruler and drawn a straight line across to the point where it meets this line. And then I've gone down to the x-axis to this point here, which tells me the mass of group 2 carbonate heated in grams, which is what I want. So if I now read off the x-axis, I read 32 grams, which is the correct answer for 1 mark. Now in the mark scheme, it would have allowed any answer between 31 to 33 grams. And that's just because it's quite fiddly to use your ruler and to get a really accurate answer. Okay, so there was a bit of leeway with that answer. Calculate the mass of the group 2 carbonate needed to produce 24 decimeters cubed of gas. Use your answer from the previous question to help you. So what that statement is telling us, use your answer from the previous question, is that we are not going to be using the graph for this question because the scale on the graph doesn't go up to 24 decimeters cubed. So what we need to do is we need to use our previous calculation. So from the last question, we established that having 5.2 decimeters cubed of gas would get you 32 grams. Now the question is asking the mass of group 2 carbonate needed to produce 24 decimeters cubed of gas. And we want to know how many grams. So let's work out how do we get from 5.2 to 2.4. Well, to work that out, I could do 24 divided by 5.2, and that gets me quite a long number, somewhere around 4.62. So to get from 5.2 to 24, I've timesed by 4.62. Now what I do to the volume, I also need to do to the mass. So I can do 32 grams times by 4.62. And if I type that in my calculator, I will get, again, quite a long number, but somewhere around 148 grams. And that is the correct answer for 2 marks. Now, there were several ways that you could have done it. The way that the mark scheme suggested to do it was to do 32 divided by 5.2 times by 24, which again would have given you 148. But the method that I've shown in purple is perfectly fine. Now, obviously, as we said with the previous question, there was a range of values allowed, given how you'd read off the graph. So for this question, a range of 143 to 153 grams was allowed. Okay, so this was a 2-mark question. 1 mark awarded for workings out, and the final mark awarded for a correct answer. A student heated different masses of a group 2 carbonate. The student measured the volume of gas produced. Figure 11 shows a graph of the student's results. The student calculates the gradient of the line, and the student makes 2 mistakes. So let's have a look at what's happening in figure 11. So we've got the volume of gas in centimetres cubed on the y-axis, and the mass of group 2 carbonate heated in grams on the x-axis. So let's look at what the student's done. So the student's looking at finding the gradient, and it says here that they've used the correct formula. So the correct formula for the gradient is the increase in volume of gas divided by the increase in the mass of group 2 metal carbonate heated, which is right because we know that gradient is rise over run. So rise is what's on the y-axis divided by run, which is what's on the x-axis. So let's have a look at the student's calculation then. So they've done 4 divided by 750, which has given them this answer. So they are saying that the increase in volume of gas is 4. Well, that's incorrect because they have shown here that the increase in volume of gas is 750. So we can also see that they've put 750 on the bottom and this 4 on the top. So hopefully you can see that actually they have inputted the numbers the wrong way round. So there's the first mistake we've spotted. So just as a quick note to myself, I'm going to write number 1, wrong way round. We're going to write the answer properly in a minute. Now the second mistake comes from finding the increase in mass of group 2 metal carbonate. Because yes, 5 minus 1 is 4, but that's not what we needed to work out here. We needed to work out 4 minus 1, right? Because where the student has constructed that triangle, the triangle starts at 4 grams, not 5 grams. So the second mistake is the student needed to do 4 minus 1, which is 3 grams. Okay then, so we have identified the 2 mistakes, and then what we need to do is we need to calculate the correct gradient. So let's write down the mistakes properly. So mistake 1, we could say something like the student has inserted the numbers incorrectly into the formula, which is what we were saying that they are the wrong way round. So inserted numbers incorrectly into the formula. Now the second mistake we said was in calculating the mass of group 2 carbonate. So they have said that the increase in mass is 4, but I'm going to say that the increase in mass is not 4, it is 3 grams, and then I'm just going to back it up saying as 4 minus 1 equals 3. Okay? So they're the 2 mistakes. We spotted them perfectly. Now we need to calculate the correct gradient of the line. Okay? So we've got the formula for the gradient. So it is the increase in volume of gas, which we're happy is 750, divided by the increase in mass, which we've now identified to be 3. Okay, so we're doing 750 divided by 3. And if you type that into your calculator, you will get an answer of 250 centimetres cubed per gram. So that was quite a tricky question, and it was worth 4 marks. The first mark was awarded for the first mistake. Second mark comes from the second mistake. Remember, you could have put those mistakes in either order. And then the final 2 marks were 1 for the working out of your calculation, and then finally for getting a correct answer of 250 centimetres cubed per gram. A student repeated the experiment with a different group 2 metal carbonate, XCO3. The relative formula mass, MR, of XCO3 is 84. And we've been given some relative atomic masses of carbon is 12 and of oxygen is 16. Now, we need to calculate the relative atomic mass of X and then, using the periodic table, name metal X. So, what do we know? Well, we know the MR of XCO3 is 84. Now, I'm going to work out the MR of just CO3. And I can work that out by using the relative atomic mass of carbon, which is 12. And we're told relative atomic mass of oxygen is 16. Now notice it's CO3, so we need 3 oxygens. Okay, so the MR of CO3, if you put that in your calculator, ends up being 60. Therefore, we can now work out the relative atomic mass of metal X by working out the difference. So by doing 84, take away 60, and that gets us 24. Okay, which is the correct relative atomic mass of metal X. So now the final thing we need to do is name metal X. So using our periodic table, we're looking for an element which has a mass number of 24. Remembering that the mass number is the big number on the top. So hopefully we can see that that is magnesium. So metal X is magnesium. So this was a 4-mark question. Okay, 1 mark was awarded for thinking to do 3 times 16, so remembering it's CO3. And then 1 mark was awarded for this whole calculation here, so 12 plus 3 times 16, getting you 60. Okay. Or you could have just put 60 to get that second mark. The 3rd mark then is getting to 24. Or showing that bit of working out, that 84 minus 60 gets you to 24. And then the final mark was for identifying metal X to be magnesium. This question is about electrolysis. A student investigates the mass of copper produced during the electrolysis of a copper chloride solution. So let's stop and think about that. So if it is a copper chloride solution, that means that the copper chloride is dissolved in water. So let's think about the ions involved. So we're going to have copper ions, right? And we're going to have chloride ions. But because it's a solution, it's dissolved in water, H2O. And we can break down H2O into being a H plus and an OH minus ion. Okay, so in this copper chloride solution, we have copper ions, chloride ions, H plus ions, and OH minus ions. Figure 12 shows the apparatus. So in figure 12, we can see this DC power supply. So this could be like a battery, which is connected to our two electrodes, right? Inert carbon electrodes, inert meaning unreactive. So we've got a positive one here and a negative one here. And they are in the copper chloride solution, as we've just discussed. Now notice that at this positive electrode, we can see bubbles forming, which implies that there is a gas being produced. And this is confirmed in the question. So this first question asks, which gas is produced at the positive electrode, which we call the anode? So, if we're thinking about the positive electrode, well, the positive electrode is going to attract negative ions. So straight away, we can rule out the copper and the hydrogen ions. So we're left to think about maybe chlorine gas or this OH minus. Well, if you think back to the priority rules of what will be formed at each electrode, a halide ion will always take priority at the anode. Therefore, the answer to this question was chlorine gas, for 1 mark. Copper is produced at the negative electrode, the cathode. What does this tell you about the reactivity of copper? So, the negative electrode is going to attract positive ions. So from what we discussed before about the ions present, we're now thinking about the copper ions and the hydrogen ions. Now the rule at the cathode is that the less reactive element will be formed. And we are told that copper is produced. Therefore, this tells us that copper is less reactive than hydrogen. Table 4 shows the students' results. So in Table 4, we can see the time in minutes. Notice that 3 is missing. We've got 1, 2, 4, and 5. And then we've got the total mass of copper produced in milligrams for experiment 1, 2, and 3. And then we calculate a mean. So, this question asks us to determine the mean mass of copper produced after 3 minutes. Now notice the command word for this question is determine, not calculate. Okay, so that's telling us that in the mark scheme, there is actually a range of possible answers that were allowed. So let's look at the pattern in the mean. So the mean at 1 minute was 0.6 and the mean at 2 minutes was 1.2. So how do you get from 0.6 to 1.2? Well, you add 0.6. So let's just try and see if that pattern's the same if we include 3 minutes. So if we're saying that at 2 minutes, it's 1.2, right? We could say that at 3 minutes, let's follow that same pattern. So let's add 0.6, and that will give us 1.8 milligrams, right? That looks about right. Let's see if that works for 4 minutes then. So let's do the same. Let's add the 0.6. And that does give us 2.4. Okay, so 1.8 would be a perfectly reasonable answer. It did say in the mark scheme to allow a range between 1.7 and 1.9 for the 1 mark. Calculate the mass X of copper produced in experiment 2 after 5 minutes. Use table 4. So I've shown table 4 beneath this question, and we are trying to work out this value here, the value of X. So how are we going to do that? Well, we've got a value of experiment 1. We're looking for the value of experiment 2. We have the value of experiment 3, and we have the mean. So let's think about how we would work out the mean. Well, to work out the mean, we add together our different values. So our value from experiment 1, which was 3.02, plus our value from experiment 2, which we're calling X, plus our value from experiment 3, which is 3.01, and then we divide that by the number of numbers. So in this case, we've done 3 experiments, so we divide by 3. And we know that that's going to give us 3.06. Okay, so let's simplify that. Let's make that look easier. So we can times both sides by 3. So that'll get rid of that big divided by 3 on the left-hand side. So that will leave us with 3.02 plus 3.01 equals 3.06 times 3, which is 9.18. Right, and that should be plus X as well on the left-hand side. So now we can simplify this, 3.02 plus 3.01, to give us 6.03 plus X equals 9.18. So therefore, X is 9.18 minus 6.03, which if you type in your calculator, gets you 3.15 milligrams. And that is the correct answer for 2 marks. You would have gained 1 mark for constructing this correct equation using the mean. And then the 2nd mark comes for having the correct answer. The copper chloride solution used in the investigation contained 300 grams per decimeter cubed of solid copper chloride dissolved in 1 decimeter cubed of water. The students used 50 centimeters cubed of copper chloride solution in each experiment. Calculate the mass of solid copper chloride used in each experiment. So to be able to answer this question, we need to be able to convert between centimeters cubed and decimeters cubed. So we need to know that there are 1,000 centimeters cubed in 1 decimeter cubed. And that's going to really help us in this question. So let's think about the information we've been given. We've been told that there are 300 grams per 1 decimeter cubed. Okay? So let's rewrite that differently, this time using centimeters cubed. So we can say 300 grams per 1,000 centimeters cubed. Now the students are using 50 centimeters cubed. And we want to know how many grams that is. What's the mass? So to get from 1000 to 50, we divide by 20. So what we've done there to the volume, we now need to do to the mass. So if we do 300 divided by 20, you get 15 grams. So we're saying that there are 15 grams per 50 centimetre cubed. Okay, and that's the correct answer for 3 marks. Now, obviously with this being a calculation question, there were lots of different ways that you could get to the answer. So you could have converted between centimetres cubed and decimetres cubed at different points. Okay, so rather than converting this here, decimetre cubed, into centimetres cubed, you could have converted the 50 centimetres cubed into decimetres cubed. So that would have meant that you did 0.05 times 300, which again would just get you the 15 grams. Or you could have converted the 300 grams into 0.3 and then times that by 50, again giving you 15 grams. Okay, so they're just 2 different ways that you could have done it, but this way that I've shown is perfectly fine for 3 marks. Okay, so you get 2 method marks and 1 mark for a correct final answer. This question is about sodium and chlorine. Figure 13 shows the positions of sodium and chlorine in the periodic table. So what we can see in figure 13 is we've got sodium here, Na, and chlorine here, Cl. The question asks us to state 1 difference and 1 similarity in the electronic structure of sodium and chlorine. So, if we look in the periodic table, we can see our groups. So remember, the groups are the vertical columns. Okay, so sodium is in group 1 and chlorine is in group 7. Now, the groups of the periodic table tell you how many electrons are in the outer shell. Okay, so we've said sodium is in group 1, therefore sodium has 1 electron in the outer shell. Chlorine is in group 7, therefore it has 7 electrons in the outer shell. Now, the horizontal rows, okay, that run like this, across the periodic table, are called the periods. Okay, and elements in the same period have the same number of shells. Now, hopefully you can see that sodium and chlorine are in the same period. Okay, they're in the same horizontal row. Therefore, they both have the same number of shells. So for my answer, 1 difference, I would write they have different numbers of electrons in their outer shells. Okay, you could specify how many, as we just did before, in their outer shells. And then for the similarity, I would say they have the same number of electron shells because they're in the same period. Sodium atoms react with chlorine atoms to produce sodium chloride, NaCl. Describe what happens when a sodium atom reacts with a chlorine atom. write about electron transfer in your answer. So, sodium is a metal and chlorine is a non-metal. Therefore, in this question, we're talking about ionic bonding, the bond which occurs between a metal and a non-metal when electrons are transferred. So, let's start by talking about what happens with sodium. So, as we've previously discussed, sodium is in group 1, so it has 1 electron in its outer shell. Now, in order to become electronically stable, sodium wants a full outer shell. And the easiest way to do that is to lose that 1 outer shell electron. And this is going to leave us with a positive ion. And the reason for this is that now there are more protons than electrons. Okay, so sodium here has lost 1 electron. And now let's think about chlorine. So as we just discussed, chlorine is in group 7. It wants a full outer shell. Okay, it wants 8 electrons. So it's going to gain an electron, which I'm going to show here in purple, therefore giving it a 1- charge. So we've now formed a negative ion because there is 1 more electron than proton. Okay, so chlorine has gained 1 electron. So now the question is, where has this electron that chlorine has gained come from? Well, this electron from on the chlorine atom has come from the sodium. So when sodium has lost its electron, chlorine has essentially picked it up to give it a full outer shell. So as a final statement, I might say the electron lost from sodium was transferred, because we need to talk about electron transfer, to chlorine. Okay? Now this was a 4-mark question. You get 1 mark for talking about sodium losing 1 electron. So 1 mark for saying sodium's going to lose an electron, and 1 mark for saying that it's going to be 1 electron it's going to lose. Then our 3rd mark comes from talking about chlorine gaining 1 electron. So again, you get 1 mark for talking about the gaining of an electron, and that 4th mark comes from specifying that it's going to be 1 electron that it's going to gain. Okay, so in this bit here we're talking about sodium, and here we're talking about chlorine. Now it is specific in the mark scheme, right, that we need to talk about chlorine, not chloride. Okay, because chloride, remember, is the ion. So chlorine is the element, chloride is the ion. The reaction between sodium and chlorine is an exothermic reaction. Complete the reaction profile for the reaction between sodium and chlorine. So we're told that it is an exothermic reaction. Well, that means that heat energy is released in the reaction. Okay? So let's think about that in terms of our reaction profile diagram. Well, that means that the relative energy of the products is going to be lower than the relative energy of the reactants. Okay, because that energy is being released into the atmosphere. So now all we need to do is join that line for the reactants and the products, and we do that using a curve. Now the curve goes up and down, forms a sort of hill shape. And if you remember, this change in energy here, we call the activation energy. Okay, and that's the minimum energy required for the reaction to take place. Okay, so it was a 2-mark question. So you needed to think about the energy of the products being lower than the energy of the reactants, and then getting that curve that goes up and then back down for 2 marks. A student plans a method to prepare pure crystals of copper sulfate. The student's method is to add 1 spatula of calcium carbonate to dilute hydrochloric acid in a beaker, and when the fizzing stops, heat the solution with a Bunsen burner until all the liquid is gone. The method contains several errors and does not produce copper sulfate crystals. Explain the improvements the student should make to the method so that pure crystals of copper sulfate are produced. So let's start by thinking about the chemicals involved. Now the student is using hydrochloric acid, but is wanting to make copper sulfate crystals. Well, really, the student should have used sulfuric acid instead of hydrochloric acid, because we need a source of sulfate ions. And because sulfuric acid is H2SO4, and an SO4 2- ion is a sulfate ion, we need the sulfuric acid to produce a sulfate rather than a chloride, which is what would be formed with hydrochloric acid. Now, the student is also using calcium carbonate solid, but wants to make copper sulfate crystals. So the student should have used copper carbonate instead of calcium carbonate. Looking back now at that same step on the method, the student said to add 1 spatula of calcium carbonate. Well, really, the student should have added that carbonate in excess to ensure that all of the acid fully reacts. Now, if we have added an excess of solid, that excess of carbonate, we now need to use a process to remove that excess solid. And this process is filtration. So the next improvement we could suggest is to filter, to remove the excess carbonate. And now to make crystals, the last improvement could be to heat gently and leave to crystallize. So this question built upon our practical skills. It was a slightly more demanding question than simply recalling a method, because we had to suggest and explain improvements to a student's method. So this was a slightly harder question. Now, as I said, it was worth 6 marks, and the marking for this question had a levelled approach. So some things the examiners were looking for was for you to identify relevant points. They wanted you to give your relevant points in detail, which is why it's an explain command word as opposed to state or describe. They were looking for your points to be logically linked, and they wanted you to give a clear account.